Hello again. This is the video for chapter 7, the second one, and I'm going to finish chapter 7 in this video. Alright, so let us get started. I hope you're doing well. So what we want to do, before I want to talk about two more ways to solve systems of equations using matrices. One is solving systems with inverses, and one is solving systems with Cramer's rule. Now they involve finding the inverse of a matrix and finding something called determinant of a matrix. I'm going to talk about, but not in details, because we just want to use the ideas to solve systems and not to do them by hand. We want to do it with calculator. So we're going to talk about the determinant of a matrix, which is that right there. It's an absolute value symbol. And then also we're going to talk about the inverse of a matrix. Okay, so let's do that, and then we're going to use it. So we know that if you have a system, 2 by 2 system, we can solve it using RREF. That means we can convert this to a matrix equation, right? So we have the matrix of coefficients on the left in order, right? Times xy equals to a matrix on the right, which is 15 and 10. Right? So we're going to call this matrix on the left here, we're going to call it A. I'm going to call this matrix with xy in it capital X. I'm going to call this capital B. So really what we have is AX equals to B. Right? So let me quickly talk about inverse of a matrix. You know that if we have 2/3 x equals to, let's say, 5, to solve this, we multiply both sides by what? By the reciprocal of 2/3, right? And we know that these two, they give you 1x equals to, well, 5 times that is 15 over 2. So that's not important. The important thing is left. How did we cancel these? Well, together, when you multiply number, right? Let's see. So when you multiply a fraction by its reciprocal, you get 1. All numbers except for 0, they have reciprocals, and when you multiply them, you get 1. So 1 is called the identity, the multiplicative identity for arithmetic. That means when you multiply two numbers, you get that identity. It also means that when you multiply that 1 by any number, you just get the number back. So it's called the identity element in multiplication. Now, there is similar concept with matrices. So let me put it right here. So with matrices, there is such a thing as inverse of matrix A, such that when I multiply on both sides, and with matrices it does matter on which side you put the matrix when you multiply. So here the matrices are square matrices, and the inverses we talk about here is the inverse of a square matrix, right? So these two, when you multiply, you get something similar to 1 in arithmetic, and you know what that is. We talked about that before. I 2 by 2 is 1 on the diagonals and 0 everywhere else. And I 3 by 3, or just I 3, has 1 on the diagonal and 0 on the main diagonal, and 0 everywhere else, like that. This, I put it in a made a mess there. Let me fix that mess. So this is 0, 1, and this is 0 here. S3, I3, and so forth. So what we get here is just I2 times A times X, times X equals to A inverse times B. Now we know that this times X is just like 1 times X, which is X. So the answer is given by what? By the inverse of the matrix times the matrix on the right hand side. Now, to find the inverse of a matrix, I quickly tell you what we have to do, but we are not going to do it. And we're going to use a calculator to find the inverse of a matrix. But basically what you want to happen is this. When you multiply, let's say we want to find the inverse of this matrix. So when I multiply this matrix by the inverse, I have to get what? I have to get I, which is this. Now this matrix, let's call it A, B, C, D. So when I multiply, I want a matrix such that when I multiply here, I get this matrix. Now it looks like we're solving two systems at the same time. See it? It's like we are solving this system with only 1 0 here, right? And then we are solving similar system with BD here and 0 1 here, right? So it's like you're solving two systems at the same time to find these numbers. And we know how to solve systems using RREF, right? So what do we do to solve this? Well, we write augmented matrix 1 1 1 negative 1, and we put 1 0 here, right? And then to solve this one, we have to do the same thing, but we put 0 1 there. Why don't we just do it at the same time? So we just put 0 1 there. So what we have to do, we have to take this, if possible, we want to convert it to a matrix that has I on this side. So we're going to make this 1 1 1 0 1, 1 1 1 negative 1 look like 1 0 0 1, 1 0 0 1. And then on this side, we're going to end up with a bunch of numbers. Let's call them E, F, G, H, right? When you go through row operations to make this look like this, you just concentrate on what? Making these look like this. And then of course you're going to change those numbers, and somehow it looks like mysteriously, but of course it's math, these turn into what you want for what? For your well, what did I call them? Why did I call them those letters when we already have letters for them? So those actually become A, B, C, D. So we can find it this way. That makes sense? So we're not going to do it this way. You could do it by hand, but I'm going to use a calculator to do this. So let me do this. So what I'm going to do, I'm going to get rid of everything. So we're going to write this as AX equals to B. And by A, of course, I mean what? I mean this matrix, 1 1 1 negative 1. And by X, I mean XY. And by B, I mean 15 10. So we're going to use a calculator, and I'm going to matrices, and go to edit. Now I'm going to create this matrix. A is a 2 by 2, so we already have it there. See, 1 1 1 negative 1 is already there. So I'm going to quit and then go to matrix again, go to edit. Now I'm going to create this matrix on the right, B, which is by, call it B. Oops. Go to matrix, go to edit, and go to B. Now I want it to be 2 by 1, right? So it's 2 by 1, and I already have 15 and 10 in there, right? So I'm going to quit. Now, Solving this by inverses means that basically what I have to do is I have to multiply both sides by, left multiply both sides by this matrix inverse. So I'm going to do that. This gives me I, and I times x is x. And so x is what? X is actually xy matrix. And I'm going to get a matrix here out of this multiplication with calculator. So I'll go to home screen and go to matrix. I'm going to fetch matrix A from here. So here we go. Matrix A. Then to find the inverse, you just use this x to negative 1 right here. See it? X to negative 1. And then you multiply it by matrix B. So go get matrix B. And then multiply. There you go. That's the answer. 12.5 and 2.5, which is exactly the same answers we have here. Right? So that's using inverses. That's how we can solve. Now, of course, not all inverses exist, and not all matrices have inverses. So what happens if the inverse doesn't exist? It would mean that the system doesn't have a solution. But it doesn't tell you whether it has many or no solution. It just says we can only conclude if A inverse does not exist, right? We can only conclude that the system has either no solution or it has many. But we cannot tell which one. But with RREF, we can tell, right? Remember? We can tell. So I'm going to talk about the other idea that is used to solve systems. And that's the idea of this guy called Cramer. So it's called Cramer's rule. So he discovered that when you solve systems of equations, there is a number that you can calculate using the entries of a matrix. And that number is called the determinant of a matrix A. And we're going to use calculator to find the determinant. But for 2 by 2, if A is a 2 by 2 matrix, the determinant actually is either you can use absolute value. Also, instead of using bracket, we use absolute value for the determinant of a matrix this way with the entry side. So you see the difference between these two. This is determinant, that's the matrix. So determinant of a matrix is defined by AD minus BC. So this number times this number minus this number times this number. And then that's it. That's the determinant. For example, determinant of A in our example, 1, 1, 1, negative 1, equals to 1 times 1 minus 1 times negative 1 minus 1 times 1. So it's the main diagonal first and then minus the other one. And that is negative 1 minus 1, which is negative 2, right? That's the determinant of this. So what does it have to do with solving systems of equations? Well, this guy discovered that if we have a system like this, then the x that we're looking for is nothing but a fraction whose denominator is the determinant of the coefficient matrix, and the same is true for y. The determinant of the coefficient matrix goes in the denominator, and the numerator is the determinant of the coefficient matrix, except to find x, think of x as the first column. The first column of the coefficient matrix, you leave it empty, you put the second column, right? It's just like that without the first column. Instead of the first column, we put the numbers on the right. All right? And then for y, we do the same thing, except this time we leave the second column empty. Y is the second column. And then we'll put these numbers on the right over here. Now, he discovered that if you find this determinant and divide it, we're going to get this x that we got here. Well, let's see if he's right. We know the denominator we just calculated is -2. And here also the denominator is -2. What's the numerator here? Well, 15 times -1 is -15, minus 1 times 10 is 10. So that's -25. -25. What's -25 divided by -2? 12.5. You got the same answer. And for this one, that's 10. 1 times 10 minus 15 times 1. That's -5. And that's what? That's 2.5, which is the same answer. So this is called Cramer's rule. Again, not the determinant is in the denominator, right? What happens if the determinant is 0? Well, again, that means that we don't have a single solution. But it doesn't tell you that whether we have no solution or we have many. So even this method is not as powerful as this one, right? That's called the Cramer's rule, and it works for 3 by 3 as well, or 4 by 4. Now again, the best method is this method here, RREF, because if we have a solution, we can tell easily. If we don't have a solution, we can tell easily. And if we have infinite number of solutions, we can tell easily. And we talked about that before. But with the determinant and the inverses, we can't. All right? So that's all I wanted to add to systems of equations, linear equations. Now we want to talk about systems of nonlinear equations, okay? Something like these, right? These systems have equations in them that are obviously not linear, not all of them. This is linear, this is not, this is not, this is not, this is not, right? How do we solve them? Well, we go back to the way that we solve systems of linear equations before we talked about matrices. So let's do that. So we use either substitution or elimination. In this case, I'm going to use elimination. So I look over here and I see I have x squared here and I have 4x squared here. If I make this -4x squared, I can add it to this and get rid of it. So let's do that. So we take the first equation and multiply it by -4. So -4 times this and -4 times 4. We are going to get this. Now we're going to take this equation and add it to this equation at the bottom. What do I mean by that? I mean you add the left side with the left side of this and add the right side to the right side of this, right? So let me clean it up. So here is the left side of that right here. That's the left side. And here is the left side of that. And then here is the right side of this. And here's the right side of this. So we add them and we get this. So y squared is 4, so y is plus or minus 2. Now, so that means that we're going to consider 2 points when y is 2 and when y is -2 and figure out what x is supposed to be, right? So we're going to use the second equation to do that. We're going to use second or first, doesn't matter. First one, we use first, is easy. So x squared plus -2 squared and x squared plus 2 squared, right, has to equal to 4. So from 2 we get x equals to 0, and from -2 we get x equal to 0. So that means in both cases the solutions are 0, 2, 0, -2. So there are two pairs of what? Ordered pairs. Two ordered pairs. Now we have to check and see if they actually work, because it's possible to get solutions that don't work. In this case, they do. So what's the geometric interpretation of this? Well, we can't really graph this yet. In pre-calculus, we're going to learn about this. This is an ellipse. And this one, of course, is a circle. You know that. But we haven't talked about ellipses and conic sections in general. We'll do that in the next chapter in pre-calculus. Okay, so now I'm just going to give you the graph. This is the ellipse, and this is the circle. So you see that they intersect at 2 points, right? And those are the 2 points that we found, 0, 2, and 0, negative 2. Okay? Now, let's do another one. This is a different one. Notice that this one had a plus here. Now we want to put a minus here. That's a different relation. So, but we use the same method. We add, multiply that by negative 4 and add, right? The same thing we just did, except we have different expression. So we end up with what? We end up with negative 13y squared equals to 20, and y squared is 20 over negative 13. Now this is a negative number, and this is a squared. So if you take the square root of both sides, we're going to end up with what? Negative in the square root, which is not a real number. Okay? So that means this system has no real solutions. So if you graph these, this is still a circle. Now this one is not an ellipse, but it's a hyperbola. I'm going to graph them and show you. Graph them and show it to you. There. This is a circle, and these are what? Hyperbolas. And they don't intersect. Now if you use programs like GeoGebra that I have used a few times before, I'm not sure why it doesn't show up. Here we go. Graph these right here for you. So we do x squared plus y squared equals to 4, which is a circle. And then the other one is 4x squared minus 9y squared equals to 36. There. And as you see, they don't intersect, right? All right. Now, systems of non-linear and linear inequalities. Now, first of all, let me give you an example of what we mean in this section by inequalities. Now, you of course, you know inequality symbols, right? So, for example, negative 2, we had compared to negative 3, we put this thing here. What does that mean? It means that negative 3 is less than, right, negative 2. Less than and greater business with negative numbers, and in fact it doesn't make sense. So is negative 3 less than negative 2? For example, does that mean that if I owe you $3, that is less than if I owe you $2? Well, no. So it gets confusing with negative numbers. So instead of less than and greater than, we're going to think of this as to the left of and to the right of. So on the number line, here is negative 3 and here is negative 2. So this statement here means that negative 3 is to the left of negative 2, and this is a true statement. Now if I put negative 3 on this side, I put negative 2 on this side, that would mean that negative 3 is to the right of negative 2 on the number line, which is not true. Negative 2 is to the left of negative 3, that's not true. So this is false, right? All right, so that's the idea. Also, this symbol, this means that, is this true? Well, yes. How do we know this is true? It's because this statement actually means 2 is less than 2, which is not true, or 2 is equal to 2. So they didn't lie to us. They said 2 is less than or equal to 2. Well, what they meant by that was this, that either of this is true. It could be both, but either of them is true, right? So, well, can't be both. I mean, can be less than and equal at the same time. So 2 is less than or equal to 2. That means either 2 less than 2, which is not true, or equal to, which is true. So we say this is true. Okay? All right, now that we know what these things mean, let me give you an inequality. So I'm sure everybody knows how to solve this inequality. Let's so that means what? That means x is greater than 2, and then you graph it like what? Say this is 2, and then you write to the right of it. But I don't want to solve it that way. I know how to solve it that way. I don't want to solve it that way. I want to solve it with a method that works for any inequality, with all of these. And that method is this. First, you turn it into an equation, regardless of whether equality is included or not. Just turn it into an equation. Then graph it. Okay, so here you go. So x minus 1 equals to 1, so x equals to 2. Now here we have only one number line, so I'm going to graph it. There you go, that's 2 and is empty circle because equality is not included. Now, second step is to pick a so what I'm going to do, I'm going to pick a test point on either of these sides. So let's pick this side. So to the left of 2. So this 2 divides the number line into two parts, right? Pick a number to the left of 2, let's say 0. And I'm going to test it in the original inequality. So x minus 1 is greater than 1. If I put a 0 there, that means negative 1 is greater than 1. Is that true? No, this is false. So we're not going to shade on this side. We're going to test point on this side. Let's say 3. So x minus 1 is greater than 1. 3 minus 1 is greater than 1. So 2 is greater than 1. Is this true? Yes. So we're going to shade on this side. Okay? All right. So that's how we solve this inequality. Now, let's apply it to something else like this. Y is greater than x minus 2. Right? What do we mean by that? Well, let's solve it the same method and we see what we mean by that. Turn it into what? An equation, right? And then we graph it. We solve it and graph it. Now, we can't solve it because there are two variables, but we can graph it. So what does the graph look like? Well, if 2, and then use the slope to go up 1, right 1. Now, graph with using or with solid line if there is either less than or equal to or greater than or equal to, less than or greater than or equal to, and graph with dotted line if there is, when I say there is where, I mean in the given inequality, if there is greater than or less than. Okay, so here we have less than, we don't have equal sign, so we're going to graph it with a dotted line or dashed line, right? Now this dashed line divides the area into what? Divides the coordinate plane into two parts, this side and this side. So again, we're going to pick a test point. Don't pick a test point on the line itself. We already took care of those points. They don't belong because equality is not included. Point on this side and on this side, either one. So let's pick 0, 0. That's the easiest one to work with. I pick that one. So that's my test point. It could be more than one test point, which is test points. So 0, 0, this is x, this is y. So we're going to test it in the original inequality. So if y is 0 and x is 0, what do we get? We get 0 greater than negative 2. Is it true? Yes, because 0 is to the right of what? Negative 2. So that means we shade on this side, right? Now, what about a point on this side? Well, let's see. This is negative 2, right? So this point for sure is on this side. So we're going to pick what? 0, negative 3 for test point. 0, negative 3. This is x, this is y. Is greater than x minus 2. 3 here. And we'll put 0 here. We get negative 3 is greater than negative 2, right? That makes sense? Is this true? No. Negative 3 is not to the right of negative 2. This is false, so we don't shade here. That is a solution for that inequality. Every point here is a solution. You pick any point that would satisfy this inequality. Okay? So that's how we solve inequalities. Now, what if we have more than one inequality? Then we have a system of inequalities. We solve them separately. We put them in the same coordinate plane, and we look at the overlap, and that would be the solution for the system. So let me show you some examples of that. Here we go. These are inequalities. So we're going to solve this separately and solve this separately, this using the same method I just described, and then see where they overlap. So let's do one of these. Now, I know we don't know how to graph these here. That's why I gave you the graphs, right? So take this, right, and set them equal to what? The right-hand side. Regardless of whether equality included or not, we do that. And then we graph. So I gave you the graph of the first one and the second one. The second one, you know, this one is a horizontal hyperbola. You can graph it by a bunch of points, but that's... So since equality is included here, I'm going to graph it with what? I'm going to graph it with a solid line. And I know this goes through here at 2, negative 2, and at 2. How do you know? Because if x is 0, y is going to be plus and minus 2. Okay? And when y is 0, x is negative 4, so negative 4. So you know that's negative 4. Okay, now, so let's get the test point for this one. A good test point is 0, 0, right? So we're going to test it in the original inequality. 0 squared minus 4 less than or equal to 0. That means negative 4 is less than or equal to 0. Is that true? Yes, that is true. So we're going to shade what? Inside here. And that's the area right here that is in blue, right? Okay, so that's that one. Now for the line, we graph it. So the line would be y equals to x minus 2. So we're going to be minus 2 is 1 point. Let me graph it with red. So the line would be that. And then we go up 1 and right 1, because the slope is 1. So we get, now, should I graph it with a dotted dashed line or a solid line? Dashed line. So this red one would be dashed. And, right? And then we do the same thing. We put a test point. The line divides the two parts. We pick a test point, 0, 0. And we test it here. 0 plus 2 is greater than 0. That means 2 is greater than 0, yes. So we shade on this side of this line. And we see the solution is what? The overlap, right? That's the solution. So the solution would be basically this part here. Even the graph belongs to this solution, right? And the line has to be dashed. The point on this line don't belong to the solution, and all of these area is good. All of this area is a solution, right? So all of these is a solution for this system of nonlinear inequality, right? And that's the same idea I just described. And again, if you use a let's say GeoGebra, let me erase those and then do it with GeoGebra. So with GeoGebra, the powerful program is you can put y squared minus 4, and then you can pick less than or equal to from here. So less than or equal to, and then x there. It graphs it and shades it for you. And then y plus 2 greater than is on the keyboard. There. Right? And the overlap right here is the solution. So computers and calculators can easily do this for us. Okay. Now, so this is, I'm going to end this video at this point. I'm going to come back here and say bye to you and see you around. This is the end of the course, and I'm sure we can finish this semester together. Take care of yourself and others. I see you around.